I've done this at least 5, 6 times. I'm not sure if your colleagues mention about me or anything, but yeah, here we are. Is there any questions you'd like to ask? Some general questions before we begin with the specifics. Yeah, let me just keep it open for 5 minutes, and then yeah. Hi, Chanelto. I know she did see her before. Aiden, yeah. Okay. Any questions before we begin? Leon? You're on 2 devices. I recommend you mute the one or leave the one. Who's Mr. Moses? Is that Mo Nice?
Yeah, that's me, sir.
I knew it. Okay, is there anything you want to ask before we begin?
No, not at the moment, sir.
Okay, cool. So do you think we should just begin and then the questions will come up?
Yes, please, sir.
Okay, cool. Let's begin. So this guy in front of you is coming from November 2025, last year's final exam. And let's start to do this one, right? I'm assuming I used to do the old lecture, going through stuff. I've been instructed that, yeah, I'm a tutor, not a lecturer. And so therefore I've changed my approach with the strength of materials. So you guys bring questions. I might do a lecture depending if there's a time. But anyway, we're going to do this. So let's quickly read. So you have an electric cable over here, which consists of copper wire with a diameter of 3 millimeters and surrounded by five bronze wires with a diameter of 25 millimeters. The copper and bronze wires have the same length, and they give us the respective elastic moduli, copper being 100, bronze being 80. So what it could look like, can I just maybe pull up a sketch, an actual image? Let me just quickly see here. Like a 3-core cable. Does anyone work in the electrical space? Anyone? Anyone changed cables before?
Yes.
Yes. Have you ever seen what the cables look like?
Yes, I have, sir.
Okay, what do they look like?
It's mainly like one big wire center in the middle, surrounded by smaller wires.
Perfect. Is it a 3-core cable or 4-core? I'm looking for, there's a 3-phase. It's just to give an image of some people, Okay, it's not exactly like this, but I mean, I'm looking now at some images here. I just want to check. I'll do a wire rope as well. Wire rope is also, sure, we've all seen a wire rope. Wire rope's also type of I wonder if they have I'll just type copper. See, copper and aluminum. Cool. Yeah, okay. I don't have exact images here. Yeah, let me not use these ones. But okay, I'll try to just paste one and then we'll obviously sketch it how we need to sketch it, what a cable might look like. Cool. It's a 4-core cable. So something like this, but obviously not like this. This is what we're looking at here. But in this case, we have so it's a copper cable surrounded by 5 bronze wires, right? So it's one there, then it's 1, 2, 3, 4, 5. Right, something like that. Sure, I have a circle shape here, Just do that again. So yeah, okay. So then we have inside this particular wire we have, yeah, small circle would like that. We've got the middle, and then we've got that five surrounded Okay. What is, okay, 1.1. We have to compute the safe load for this cable, assuming the allowable stress in the branch is 60 megapascal. So that's perfect. So when you see an arrangement like this, right, what do you think of in terms of module one, series or parallel? What do you think this is?
Isn't this in parallel, sir?
Yeah, that's correct. Is there a reason why you say that?
Because the bigger wire of 3 mil is inside of the other wire surrounding it.
That's also one way. So I'm just gonna do a sketch here. That's okay. Let's just assume I'm just doing a cross-section type thing, right? So we can see it over here. So obviously it's being surrounded by the other wires. The way we want to view it is that if this thing is loaded, right? Let's say it's on a transmission line, this force is being shared by that and being shared by the 5 copper wires. Is everyone with me? So when we have a total force and it's distributed and it's shared by two or three or four, 5 different structural elements or whatever you want to call it, it's basically a parallel setup. In this case, our F1, F2, we could also call it F copper and F bronze, right? But obviously we know this must be, it's like 5 times the area of whatever. So I hope could everyone identify that it was a parallel arrangement, because that's the first step. Rosal, Sydney, Chanel. We all see that at least. That's the first one. You guys got to talk to me, eh? Can't be talking to myself here. Dion, could you see that?
Yes.
Okay. So then let's start to move on. So typically for these type of questions, I'm sure you guys are aware of the other ratio, which is going to be, I'll come over here, is your extension in the one is it's equal to the extension in the other one. So it's like this. Obviously, this is the standard conditions for parallel arrangement, right? And this is given that the lengths are the same, right? They will both elongate by the same amount of the same distance. Therefore, let's quickly see. So, what school of this equation are you guys familiar with? You can express this equation like there's 2 ways to do it, right? You can say, you know that your how do I say? We could do the strain one. You guys know the strain one, where we could say the strain in that is equal to the strain in the copper. Are you familiar with that one as well? Talk to me, guys. If you're unsure, please let me know. It's not me being cool and solving these problems. I mean, I can solve them. Yeah. Are you familiar with that relationship?
No, we are not, sir.
Okay, cool. So I just want to quickly maybe check the textbook and I can show you where it is. So that could make this question very easy. But I'm sure for now, let's quickly try this. So your extensions are the same. We can also do the flea thing, right? You know this one? FLEA. I'm sure you guys are aware of this. Are you guys aware of this?
Yes.
Okay.
Yes, sir. Yes.
Perfect. So if you look at this thing properly, you'll notice we have an F over A, and then F over A we can immediately place by stress. Am I right? So we have stress L over E. This is for the bronze. Do you guys agree with me? Can you see that? F over A will be stress over here on top. We have L over E. And we all see that. The reason why I'm good at a lot of these things is because I'm good at maths. So that helps me a lot. Okay. Are you all happy with that? Can we see that? That's going to help us already now with they give us the allowable stress in the bronze. Can we see that? if force divided by area is stress, right? Which is that there. Force divided by area, stress. Are we happy? What I'll then do is, because the lengths are the same, if I divide L here, I divide by L here, I must divide by L here. And if I do that, it's the same value of L. I'm basically left with stress over E. Let me just keep it all bronze over here. Bronze, and the side is going to be stress over copper, stress over elastic modulus. So cool to everyone. Can we all see what I did there? And the reason why I'm doing this is because I was already given the stress for bronze. And I have the elastic modulus, so therefore I can easily compute the stress in the copper. Is there any unclarity?
No, sir.
I'll give it a minute. Yeah. Let me know. You can say yes, you can say no.
No, sir.
Okay. Show you the other one that you must do also. I'm sure if you've done the textbook, you've probably picked up one similar to this, no? There's one of the steel and the bronze around. Okay, so let's quickly see now. What's next if we just populate those values, the respective values into this equation. So in this case, we have our stress in bronze was given as 60 megapascals. I'm coming over here. So that's 60 megapascals. Our modulus, elastic modulus, or Young's modulus is 80 GPa. In this case, normally with these questions, you have to find the stress. In this case, they're giving us the stress, and we need to find the total load. That's what's happening over here. That's the safe load for the cable, the F total in this case. I should have mentioned that, but anyway. And then we need the stress in the copper, and then we're dividing that out by this. So I'll probably repeat this again. And when you guys solve it, so they want the safe load for this cable, and the safe load for this cable is obviously the total load this cable can carry, which is comprised of both the force within the copper and then also the bronze wire surrounding it. So that's the total force for the cable. So that's what we're actually looking for. So obviously, before we get the forces, we need the stresses. Typically, it's done the other way around. We'll be given the forces, and we have to find the individual forces and then find the stresses. But anyway, let's quickly find I want you guys to solve this for me quickly. What's my stress for copper? That's why you guys are here. I've got the stress. Am I getting the stress in the copper? Am I able to get it? Yeah, I am. Now thinking. Got the memo somewhere, yeah. I've seen it before. So what's the stress in the copper? This is a 9, eh? I hope you guys are not just listening to me. You guys are busy solving. Hi, Saji, how are you doing? One of my other top students.
At 75,000 kilopascal, sir.
Nah, so it's stress, we don't talk kilopascal, we only talk MPa. So give me the MPa value. Should I show you? Should I show you? Well, okay, let me just show you. Right, my first session with you. So let me be kind here. Share, and I go to screen. Can you guys see my screen? I'm going to pull up this calculator quickly. Okay, can you guys see my calculator? Mr. Moses, yeah, cool. You guys can talk, eh?
Yes.
Yeah.
Yes,
So,
I can see it.
okay, it should, if you can't see the whole screen, the calculator should be there. Mr. Moses, can you see it? Kuma?
Yes, okay, sir.
Cool. If you can't see it, the screen,
Yes,
you probably have to refresh your whole screen. Anyway, let's quickly do the calculation. So I'm saying 60. This is the way I do it. I go 60. You can say I use this over here, right? like that. I'm assuming you have a Casio. If you don't have a Casio, get a Casio. We're timesing, that's by 80 GPA. Super easy to type in the calculator. And then we're multiplying that guy by the 100, right? Click on 100, go it like that, you press equal, you get this. Why is it so suspicious? It's 75 kilopascals. That's a bit suspicious, eh? Am I doing something wrong here? Let me just check. Oh, no. This is power 9. This is power 9. There we go. That should be. So I just press that guy over there, and that's 75 MPa. By the way, remember the M. The M means 10 to the power 6. Are we all happy with that?
Yes, sir.
Okay. So when you talk, typically this is the case. When you talk fluid pressure, right? Fluid pressure, we're talking KPA. It's pressure is pressure. Don't get me wrong, right? And yeah, don't worry. We're talking material, the same type of thing. We're talking MPa. But Pascal is Pascal, pressure is pressure. It's force over per unit area. Yes.
If I wrote the answer like 7.5, would it been wrong?
Nope, it's correct.
Okay.
So that could be 7.5 watt times 10 to the power 7 or something. It's still fine as long as you have enough zeros there. Yeah.
But say if I didn't write it 10 times 10, just write 7.5. And
no, that's completely wrong because 7.5 means 7.5, not 7.5. You know what I mean? A lot of zeros.
But don't get like a half a mark or so. It's just wrong.
Nah, no ways, man. In engineering, you have to be very precise.
Okay.
Yeah. There's a big difference between 7 billion rand and 7 and 5 cents, so 50 cents. I'm sure you know what I mean.
Yeah.
Yeah. The zeros matter in magnitude. Okay, so once it is done, you're going to find that safe load, right? But bear in mind, with our safe load, we've got 5 cables on the one side. So if you remember your basic formula, F total is equal to F1 plus F2. Ahmed, okay. It's F copper, F bronze. But that being said, our total force, okay, we'll do it now. So we know that stress is equal to force over area, and therefore stress times area is equal to force. Is it clear with everyone? So then we can say stress copper, stress area plus stress, what's it, bronze, and then area bronze. However, our area, total area for the bronze is 5 wires, right? So we're going to times this by 5. So this area is times by 5, basically, right? It makes sense. We imagine it as one big area. So what you then can do is a simple plug and play type thing over here. So you have 2 choices. You can either work out the areas individually, which I think we should do. So let's do area copper and area bronze. So I'm sure you guys know your area for a cylinder, right, or a wire is pi over 4 times.
No, not now. No, my friend, every day only 20 days cashback, I don't give that. My job is help. I understand cashback, not report it. Understand?
So pi over 4 times pi over 4 times. I actually want to listen to that. I'm not gonna lie. Pi over 4 times 3 millimeters, right? Okay. So that's like that. We're gonna square this guy, am I right? And then the other area was 2.5 millimeters. That's for the bronze. Okay, is that fine? So can you guys just get me these areas for each one?
So the area for the steel wire would be 7 times 10 to the power negative 6.
You mean the copper one?
meters.
Is it the copper one?
No, that's the steel. The steel, sir.
There's no steel in this case, man. Remember, it's bronze. It's copper and bronze.
Oh yeah, sorry, the copper. I mean the 3 millimeter.
Yes. How much is it?
It's 7 times 10 to the power of negative 6.
Clean.
Not clean, but that's what I wrote.
No, it should be clean, like 7 point something.
I got maybe it's 7.06.
Okay, yeah, include the decimals there.
I got
7.069.
Yeah, okay.
Yeah,
Okay, perfect.
7,069. Yeah.
Yeah, try to operate within 3 decimal places. Yeah. What is this? -6, eh? Meters squared. And then just do the, what's this guy? The bronze. The bronze will times by 5 upwards.
So I got it as 2.4 times 10 to the power of -5. So
Okay, that's fine. Meters squared. No other units? It's all right, I will set that. That's not a problem. Okay.
Sir,
wait.
can I
Yes.
ask
Who is that?
on the area for bronze, Kagiso,
Oh, Kagiso, yes.
we are using the 2.5 millimeters.
That is correct. It's coming from here. Kagiso. Can you see over there?
So I got a different answer from the one you guys got.
Then give me your answer. I didn't get this one.
I got 4.909 times 10 to
I
the
also
power.
got that answer.
Okay, so that means you can't trust a Monice, no? Yeah. It's like that sometimes.
Yes, I got the same answer.
It's like that. So let's equal 4.9. There we go. Thank you,
Yeah.
Kagiso.
Thank you.
Someone named Monice, I should have known better. You see this? It's the red flags they appear, but we Mr. Moses, you got that? Where is it? What was it? 4.9 again?
4.909 times
Okay,
10
that's
to the
fine.
power negative 6.
Okay, perfect. Okay.
sorry, sir, shouldn't we multiply it by
I didn't
5?
say you multiplied it by 5. That's why you
Oh,
got that point.
okay, I see. We'll do the 5 over here.
Yes.
We'll do the 5 here. Are you with me? I'm gonna come here.
Oh,
Yeah,
okay.
yeah. So we can do it before or after. I'm just doing it separately, man. I'm being very, very thorough here. I will try to be less thorough moving forward. Don't worry. So then once we have our stresses,
You said I was wrong, sir.
I take it back, man. You take all my qualifications. 75 megapascals times Kagiso, bly maar. 069 -6 plus what's bronze? Bronze was a 16, no? Yeah. Okay. And then we times by Mo's answer, which was, what was it again? Was it 2 point, what was it?
2.45 times 10 to the power of -5.
Perfect. Okay, there we go. So we do this, and therefore we get the total. I hope everyone has got the concept. That's what's key. Yeah? It's the concept. Now let's find the total safe load now.
So I got an answer of 530.97 kilonewtons.
Okay. I'll check. Kagiso will check for you. As soon as she's will verify. That looks very high, eh? No wonder. That's a big load for thin cables, Mr. Moses. Because it's like wires. Yeah, wires shouldn't reach the kilonewton range like that. So I mean 530 kilonewtons is like, you convert that into mass, it's wild, man. Let me check here. Give it a 9.81. Oh, that's kilos. That's like 54 tons. No, like that's 1,000. So I doubt. Yeah, it's no. This value is too big. Please check. I'll just do the first one and check. 7.096. The first one should be 530. So I don't know where this man is getting 530. So this one is 530. This piece over here, 530 something. What's it? 530.175. So can you please just check? So what is your total answer? Is it a Pakistani shopkeeper? Huh? Leon. Lagiso, are you done?
No, sir.
Okay.
Almost.
Okay. Antonio Pina, are you done?
So, correct me if I'm wrong, sir, but
Yeah.
the values that I'm getting from the on-screen values, I get 1.9 million, sir, newtons.
Let's have a look. Lagiso is just enjoying that, it seems. So let's quickly see 60, right, times, I'm doing the second piece right now. So it's 60 times 2.45, is it right? Times 10 to the negative 5. Just check my calculation over here. That's 147. I don't know how you're getting the million.
1472.
Yeah,
Yes, I also got
1472.
that.
Then why aren't you guys saying
1470.
anything? Yeah, okay. So we just simply add the two together. That's 530. And that's 175. All right. Mr. Moses, do you see where you made a mistake? So it's 2000 newtons. Yeah, there we go.
Yes.
Okay. 2000 point something newtons, right? Okay.
Shit.
Yes. Yeah, that's how you lose marks in the exam, no? Okay. Is there any questions before I proceed? Any questions, guys?
Sir, can I ask this? This answer we just calculated is for 1.2.
No. So this one is 1.1. This is the safe load for the cable.
Oh, okay.
You understand?
Okay.
It's a total load the cable can carry.
Okay.
Yeah. Yes.
Thank you.
It's a lot to say with something like this, but okay, let's quickly do this. So it says the extension in the cable over a length of 45 meters. Okay, so let's quickly do that. So if you recall what I said to you, the extension is the same for both, right? So therefore, and we have the equation for extension right in front of us. And we can verify with either the copper or the bronze. It makes no difference. So this is 1.2. Okay. So extension in the copper will be FLEA. Alternatively, as I said, we have force over area, which is stress. And then we can just say L over E. So we have options over here, right? We can use either this or that, but in the case that we have the stress values, we should just obviously use the stress values. It's just going to be easier this way. Or let's do the force one. So luckily we did find the force, I believe, for the, what is this guy? For the copper. So let's plug that in. So it's going to be 530.175. Our length was given as 45 meters, right? We divide that by E for copper, which is equal to 100 gigapascals. And then we're timesing that by the area, which was also given there. And that area is the area of 7.09. Yeah. 7.0. What's it? 69 times 10 to the power. What is it again here? 6. Okay, here we go. And let's get the extension. And I want to be clear to you, you can find the extension also using the bronze as well. using exactly the same setup. It'll come out to exactly the same answer. So let's find the extension. I want to show you what this might look like. I'm not sure if you guys will see my screen. Transmission line. Transmission line. Yeah, it could be a line, 45-meter long line. Something like this. Obviously, yeah, we're looking at the mechanical structure integrity. I don't know if you guys can see my sketch over here, but in strength of materials N6, you look at something called catenaries, and you look at, I think, yeah. So the line would be a bit long, and you've got a bit of a. Nevertheless, let's quickly get the extension there. So we can see our next question. Oh, someone had activity there. Okay, let me try that one. So Moses, you got the Leon, you got the Razi, you got the extension for us? Puma, Eden. Yeah, talk. Don't be shy. You guys doubting yourself now? If you lost, you can easily just ask, eh? Sazi. Mr. May. You guys talk. I can see you guys talking, but then it goes
Can you hear
away.
me? Can you hear me, sir?
I can hear you, Sazi. Yes.
Oh no, sir, I'm driving. That's why I'm not engaging so much, but I'm getting the concept.
Okay, noted. Okay.
Yeah, I have my books all with me. So
Okay. No stress.
That's 134,004.
It could be, is that what's my unit?
Now that's got 34,0046.
I'm not sure. And the colleagues corroborated answer. 34, 0,
046.
046 times 10 to the negative, or is it meters or?
I just punched everything in the calculator and I got that. There was no times 10 or
Nah, it cannot be. You're saying it's elongating by 34 meters.
yeah,
That's crazy.
Saying.
Yeah, it cannot be that. Yeah.
Millimeters.
It's millimeters. Yeah. What's that now? Let me just see. Yeah. Times 45 times 7.069 times -6. Cool. And you should get, yeah, 0.03375. Do you guys see that there? Let's do that.
Yes, sir.
Yeah, that's your answer. Okay. And that's in meters. Of course, you can easily convert that into, what is this called now? Yeah, millimeters, exactly. So that's going to be 0.03375. And that's perfect. If you got that, well done.
Yeah, went wrong. Yeah, I see.
Did you see where you get wrong?
Yeah, I didn't put the comma there, but 534,179.
Okay.
It is a
It's-
1.
Remember, it's coming from this force over here. You see it? Yeah, don't please don't copy my handwriting, man. I don't trust myself sometimes. So it's better you follow the concept. All right. Is there any questions before I do the next one? So I'm just going to open Snapify. Snapify. Yeah, so if you look at this, what we just did was something similar to this over here. That's in the textbook page 43. But in this case, they wanted to find the stresses. So yeah. Anyway, this is some good practice for something similar to that. But then someone said they wanted us to do activity 2, right? Now, why can't I open my index? So let me just go to activity 2 and then activity 2 something. It's this one. 2. What was it again? 2.1. Was it Mr. Moses? Was it this one here?
Yes, sir.
Okay, cool. Let's do that one and see. This one's a very wordy one, but it shouldn't be that tough. So let me just do it here. Okay, paste him here. Okay, cool. So obviously, I'm assuming you went over the underlying theory to tackle this problem, and it's gradually applied, and so therefore it should be an easier case to deal with. But anyway, let's see if I can solve this one. It says a metal bar with a diameter of 20 millimeters has a length of 2.2. If the stress at the elastic limit is 140 megapascals, what is its proof resilience? What is the strain energy? So let me just start over there. Your strain energy formula, I think it's been derived for you. It's that one. The strain energy stuff, yeah, it does get used, but I don't think the syllabus in the TVET colleges gets there. But it's F squared L over 2AE, right? This is the energy due to the deformation, okay? Deformation or whatever the case is, yeah. Really important concept is concept of energy, but nevertheless. The other alternative, I think, am I forgetting something? No. Yeah, okay, so yeah, you have another alternative. I'm just checking the textbook. You can also use the stress squared over V over 2E. Are you familiar with this? This tells you the so-called strain energy. Are you familiar with this concept?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So based on this already, can you see we can actually, they're asking what is proof resilience? Can you see we have the stress within elastic limit? We've got the diameter and we've got the length. I believe from that we're actually able to find the volume, right? Which is cylinder, right? So that's sorted there. Then it says, calculate the maximum value of the suddenly applied load so that the elastic limit is no more than the allowed. All right, fine. Then say, also determine the gradually applied load needed to produce the same extension as the suddenly applied load. This is a very wordy question. I don't see it typically in the exams. But nevertheless, let's try. So once we find our strain energy, what we're then going to do, let me just see here, is it 2.1, right? We obviously for the next 2 parts we need to find the forces, and then from the forces we will yes. Let me just talk to me.
I just wanted to ask a question, sir. In that scenario, when they refer to the elastic limit, right, sir?
Okay. Yes, that
is that the stress caused by the gradually applied load? If I may pull.
Yeah. So what's key of this whole thing now? If you've done the first section, it's a very good question. You see this graph, your standard carbon steel graph. You see this whole region here, right?
Yes.
You see the region, that's the elastic region. These theories or these maths only are based within this region. This is called the elastic region. It just start over there. Okay. This other region from here to here is called the plastic region. There are a lot of advanced theories how to model materials here, but this is out of the scope, which you don't have to worry. So we're over here. Okay. So you are asking me, by the way, the area under this graph, right, which is the force and extension graph. So you approximate this to be a triangle. The energy will basically be half Fx. I'm not sure if you're familiar with this. This is the work done. You know, like if you guys done
Yes,
sprints.
sir,
Yes, perfect.
yes.
Okay. So now you're asking me, so you see the thing with the F, and I'm gonna show you some practical stuff where these are actually, and I'm teaching a subject similar, not like this, but it's there. But you're asking me what force gave you that stress? Is that what you're asking?
Yes, sir. And to your equation that you just expressed over there, sir, that
Yes.
shows me that the elastic limit some stress is caused by a gradually applied load because it's 2 times less.
Yes.
Then,
And so, okay, so before we get there, we're gonna get to that part still. But they're giving us defined values already, man. Are you with me? Which you want to operate within here.
Yes, I fully understand, sir.
Yeah. And then we're gonna go to the next part, and then we can discuss. Let's just quickly see. Let's get the strain energy first, but it's a great question. So we just chop in the 140 here. This is one of those questions I probably would have flunked myself with all the amount of words. But anyway, 0.02 times that by 2.2. And then we divide this by 2, and then you have a 205. Let's get the strain energy. Huh? I believe the answer at the back of the book somewhere. Okay. And then based on that, I don't think we still need to find the force here. We're going to find that force. Yeah. We'll do the force afterwards.
I believe it's 33.04 joules, sir.
Okay, yeah, that seems okay. Okay, Kagiso, can you verify for us? What else is there?
Say, I'm
Yes.
still lost.
Okay.
I'm lost.
Have you done module 2 before?
Kind of.
Okay, that's why. No, no worries. No judging. Yeah, don't stress about it. So yeah, it's module 2 basically.
Okay.
Okay, cool. So I think if anyone wants to, I can proceed now. So the next part is calculate the maximum value of the suddenly applied. I'll send you, by the way, I'll send you the other recording for module 2 to get you going. I hope it'll be useful. So calculate the maximum value of the suddenly applied load, so the elastic limit is not more than allowed. So what is nice here, what they're telling you here, is that it's the same load within that elastic limit, right? So let's do that quickly. So what we need to just basically find is force equals stress over area, right? That's the first thing we find. Once you find that force, we've got to actually look at this as well. So let's just quickly do a small mention. And I did post it on the group. If you can see here, for a suddenly applied load, okay, this is suddenly applied load, that's 2 times the weight. Okay, I'm not sure if you guys have seen this. You see there? So once we find that, oh, this is the stress max. Can you see over here? Can we say stress max equals 2WA? Let's do that one there. So then we're gonna find the one to force, which is W. Okay, let's use this one. That's a lot better. So like I said, it's not that confusing, man. It's just that we started like this. What was it again? Stress equals 2W, no? 2WA. Okay. So then now all we must do is solve for W. That is the load they're talking about. And the reason why it's 2 times, but that's because it's suddenly applied, right? That's an impact load. Okay. So let's quickly see 140. Chuck that in here. We've got it to the W we're looking for. And then we need that area. The area will be the pi over 4 times 0.02 squared. Okay. Let's solve for W over here. I hope you're following the ones who know. Yeah. Should be easy to solve, no? Okay, just go right there. Just keep it like this. Let's get that W. And we can actually do the gradual applied now already, man, because once we get the other one, and then it's just a case of
I'm getting 21.991 kilonewtons.
yeah, I think that's correct. Yeah, 21.991. College, can you check? And then if you want the gradual one will be just half of that. I don't know if you guys are aware of that. Or sorry, man, not half. It'll be double the amount of load. Yes. Excuse me? I can't hear you.
For the gradually applied load,
Yes.
F is equal to W.
Yes, that's correct. But we have 2 times W. That is the suddenly applied one now.
Suddenly, yes.
So
I was
that
just confirming that, yes.
Sorry?
I was just confirming.
Okay, yes. So 2 times, I'll go over it now. So then obviously that W, right? If we're gonna find the gradual applied is basically the same, but it's just the normal force over area or W over area. But you're not timesing it by 2. So this would be 140, and I'll explain to you what this is about. You'll find W and then you'll find this. But obviously, if you're smart about it, you can see that this will be 2, that's a half of the other one. The reason you'll notice. Okay, let's find W and then I'll talk the theory. Yes. Talk to me. What was that now? Okay, anyway. Let's just quickly get the W, then I'll talk the theory. Yeah. I'll show you what I'm talking about. Yeah. The idea of this is that a suddenly applied load can have a lesser magnitude in terms of the force, right? But it can bring a big amount of stress because of the way it's applied. But these equations don't do it justice in terms of me mentioning this. So yeah.
So I get 43.982 kilonewtons.
Yeah, that's fine. So gradual applied load for the same amount of stress, we require a bigger load. What's not given here is the time impact of a suddenly applied load. I think I did it prompt, so you can actually see the difference. Impact load is a smaller load in magnitude, but the stress is still the same because of how quickly it's applied. I mean, it's like a punch. You know what I mean? It's a big difference between, if you would imagine, so you punch someone quickly. The stress is the same, but versus you digging your fist into someone, you're putting more force in, trying to get the same stress. It's a similar idea when you're looking at punching operations or putting top of bottle caps, that kind of thing, at conveyor type plants and stuff. But that's this question anyway. Okay. Yeah, I don't think everyone has covered module 2 well, but anyway, that's that. Let me just check the next one. Is there any questions before I move on, guys? So maybe we can talk to some theory before I actually move on. Achisa, do you have any questions? Chanel, Sazi, Leon. That's the next one.
Sir, if I may say something.
Yes, of course.
The one thing you just cleared up about my uncertainty about this specific topic, sir, is that I see you used the stress at the elastic limit in both the suddenly applied loads equation and the gradually applied load. Now, that was the only thing that I
No, I get you.
Had the struggle with, because I thought with a suddenly applied load, because of its force being twice as much, it would mean that its stress caused by that force would also be a different value, sir.
No, I'm with you, man. This is a very wordy question, man. If you know what I mean. It's not like I don't want to say like an engineering type question. I think Have you guys done example 2.9? It's a very good example. Maybe I should do that
I have
one.
not, sir.
Yeah, let me quickly do that one. For example, 2.10, that's also another good one. Yeah, in terms of explaining the difference between the two, man. Let me quickly see. Yeah, but 2. Okay, yeah, I'll try my best. 2.9, example 2.9. Not sure if I've done a video on that one. Okay. So what I like about it, and I recommend everyone to do these ones, is it goes over, yeah, like this one. Can you see here? We've got this setup, which for the life of me, I've never experienced in my life. But I guess it's a punching type operation, could be something else. I can show you where this other theories come from. But anyway, so here we have what I want is a maximum stress in the ball, right? If the load is gradually applied, if the load is suddenly applied, and the load is to fall from a height of, it's an impact load at C, fall from height of 100 onto the collar. So we're looking at the stress within the ball. Okay, just quickly on screen this. And obviously, you'll notice that the stress will increase depending on the condition of the loading. I hope everyone's clear with that, no? Does it make sense to everyone?
Yes.
Yeah. The section is useful, but yeah, it's anyway. Okay, let me just put that there. Bring this down. All right, so let's do this. So we have 3. Let me pull up my strain energy slide here. I can find it. Yeah. A lot of these topics is useful in something called mechanical design. Okay, here are some slides. And what I'm looking for is this table over here. And so this essentially tells us, I wonder if this can work out. Yeah, let me quickly see. So let me just copy, let me just put on screen this. Yeah, so this is the whole topic in essence, right? Okay, just make that smaller for you. And yeah, I believe it's all scattered. They call it P. It's also called W. You know what I mean? Same thing. Just variable semantics. Okay. So let's quickly do the first one. So the first one, when the load is gradually applied, right? It's a simple W over A, right? Is everyone with me? It's a situation that you know, it's gradually applied, right? There's no impact. So in this case, W is 30 kilonewtons. And then we divide by each respective area. So it's pi over 4 times 0.03 squared. Can I just quickly get you the answer? All right. Straightforward.
7,0686.
7,068. 7,068. Is it 70? What is it?
It's 7,0686.
Okay. Let me just check that out. Are you sure that's right?
I've got 706.
I want the stress. I'm looking for the stress, not the area. I want the actual stress. Yeah.
No, then that's 42,411 megapascals, sir.
42,11. Could we all get that?
42,411.
411 megapascals. Perfect. Obviously, for B, that's suddenly applied, right? Straightforward. We're just timesing the same thing by 2. So we're just going to times whatever we had by 2. Are we all happy with that, colleagues, right? So that's going to be like 84.88 something, right? So we're just timesing this by 2. It's the same stuff. Nothing has changed. Can you see that? That by 2. So it's 84.8 something, right? 8.
Yes, sir.
2, right?
48,882.
882. So this is 441. Okay. Yeah, case in point of more stress will be induced in the material. Let me just clean it up there. When you guys do when's the assignment due again? Just remind me.
We get it on Tuesday, I think, and then it's due the following day.
Okay, cool. It's not tough, don't worry. So the next one is a load. If the load is applied, if the load is allowed to fall a height of 100. This is like one of the standard questions. So let me break it down the first principle way here. So how they model the situation or produce it is they look at it in the case of energy, right? So they look at the case of potential energy equals the potential energy loss is equal to the strain energy gain, right? Okay, lost and then gained. So in this case, the gravitational potential energy, the mgh thing, and we know your strain thing, your strain energy, as you know now, right? Which is going to be stress squared A over L over 2E, which is essentially coming from the previous question, if you recall, right? That equation over here. Was it 2V? So it's V, no? So it's V. Okay. Oh, same thing. ALV, same thing, right? That's fine. That is V. Yeah. So now the only thing which you need to account for is when this collar drops, right? What you're going to find is that this bar is going to increase a bit. Can we all imagine that? I should ask AI to actually do something like that. So as this load falls down here, right? Obviously, like in an impact fall, what we're going to find is that this bar is going to extend a bit. And then that's going to be at the bottom. There'll be some kind of deflection. You know what I'm saying to you? Are you with me, colleagues? Yeah. So it's the full 100 mole, but then there's going to be an extra amount of deflection it's gonna experience. Is that correct? Can you agree with that? So this equation must be now modified by the h is going to fall by that small extension which we don't know. Is that clear to everyone? I'll check if I can pull something like that off. So as it falls, it extends a bit.
Can you please repeat again?
Okay, let me see if the book has something. You know, maybe my drawing is very suspicious. You know, so that's that. It looks similar to that. Yes, like this. Can you see that? Is that Kagiso? You're asking that. So as the mass falls down, right, you'll notice that the thing will extend a bit. Yeah, this is a series bar now, but I think you understand what I'm trying to say. Just imagine it was one. Okay, yeah, this is perfect. You see that as that drops, right, an extension will come. I'm talking about an impact drop, not a slow drop. You know, it knocks quickly. So the height goes, plus there'll be a small extension, which will give us the h plus x. That's what most students miss. You got that, Kagiso? That is you. Okay, maybe not. And so then in the end, we basically end off with that same setup over here. This doesn't change for any of these cases. Once you see a bar with a mass on top, you're dealing with this setup over here. That's stock standard. Okay, so now we must find a stress here, right? But the problem is we need to replace that x with FLEA. And again, we can change this guy to the stress L over E. This force over area E stress. Okay, let's quickly do that. So then we have mg, then we have stress, sorry, we have h. We have a question you can ask like that. And then we have stress squared, then we're going to have A, we're going to have L, we're going to have 2E. I know that this can work anyway. Let's see the simplified version of that, but we'll check. So let's quickly populate these values and let's see what we're going to get, right? So our mass given was 30 kilonewtons. It's given over there, right? So you got 30 times 9,81. It fell through a height of 100 millimeters. Okay, it's 0.1. Plus the stress we're looking for, we don't know. we have the length given to us as 8 meters. And then we have our elastic modulus, which is given as 208 gigapascal. Cool. That is equal to some stress squared, which we're looking for. Can you see there's a stress and a stress? We need to find the area. And I think someone gave me that area. What is the area again? 2 times. Can someone just give me that area? I know the length is 8.
Area was 706,858 times 10 to the negative 6.
Perfect. So what I want you to do now, it's quite simple. I want you to find what this is. This should be stress squared. So all you're going to do is say all of that divided by that, we're going to get a coefficient over here. Can you first do this piece for me over here? Let's get that piece over there. Okay. And then we'll do the next. Yeah. So I wanted 706.858 times 10 to the power negative 6 times 8 divided by 2 times 208 times 10 to the power 9. Welcome to Strength of Materials in 5. Let's do this.
Sorry, sir, for the stress squared.
Yes.
Getting 1.359 times 10 to the power of negative 14.
Negative 14. Yeah. 9 minus 6. Okay, it's possible. Yeah. Okay. That's cool. I hope that's correct. And then the next one is.
I got the same thing, sir.
Okay, perfect. So you want to times this over here, and then you want to times this over here. You're gonna see where we're gonna get to now, right? So I want 30 times 30 kilonewton times 9.81 times 0.1. Can I first get that one over here? That's the first one you want to do. Right?
So, sir, the 30 kilonewtons times 0.98
Yes. Brother. Yeah.
times the 0.1, so would be 29,400. Yeah.
29,000.
400, sir.
Like 29,400 like this.
Yeah, sir.
You're not used to big money, Mr. Moses. Still getting used to it. And then the next one is the stress coefficient, and that'll basically just be this over here, right? So let me use this one.
Sorry, excuse me, sir.
Yes, that 8 divided by 208, yeah. Yes.
What is that value? The first one.
This one or this one? Which one? This one, yeah.
Okay, I can't see your cursor now. Okay.
This one.
On top.
There.
On top. The first one on the left.
This one.
Yes. The first
That's
one.
right.
Yes, the first.
This one, yeah.
I'm
That
having
one.
trouble.
This one.
The
The 706.
one on the red marker, the one we timesing by times 9.81.
Oh, the 0.1. So this
The mass.
is
The mass, sorry.
30 kilonewtons.
30. Okay.
Yeah, sorry.
Thank you.
Oh, I understand.
Sorry.
I get you. So, Mr. Moses, do you have this coefficient for us here?
Sir, I got that as 1.1772 times 10 to the power of negative 5.
Okay, sorry about that. Just bear with me quickly. I just when I 1 point, yes.
1.1772 multiplied by 10 to the power of -5.
-5, huh? Okay. Okay, wait, so you made sure you made sure you times all of this by 8 divided by that, right?
I hope so, so yes.
Okay, so let me just confirm. Being good at math is of utmost importance, man. I mean, engineering, yeah, hands-on is a big factor as well. But a lot of engineering is just being good with some calculation, because we use calculations to make decisions. But I get 131. I write it down. 30 times 9.81 times 8
Same.
divided by 2.
I also get the same answer.
But you said nothing.
I was still calculating. Yes, sorry.
You see, this is why the tenders are being eaten, because people are not saying anything. Okay, so what was it again? 1 point what, Kagiso?
1.132 times 10 to the power 9. -5. Sorry.
Okay, is that fine? No, five.
-5.
Fine.
Yes,
Thanks.
-5.
Thanks, Kagiso. Mr. Moses, you have a look at that. So over here, guys, can you see what this is here? Right? If you slip, this looks like a standard quadratic equation, right?
Yeah.
But in this case, our x is our sigma value, right? So let me rearrange it nicely for you by carrying over things. We have stress squared, 1.359 times 10 to the -14. If I carry this over, that'll be negative. So I'm carrying this guy over there, and that's 1.132 times 10 to the -5. And I'm carrying this guy over there, that's minus 29,400, and that's equal to 0. What we then apply is Old Faithful, where sigma is going to be minus b plus minus b squared minus 4ac. You probably thought you're not going to use this again. Well, here you are. So you're going to put all these values into the calculator now, and you're going to get two stress values of the tensile, a positive one and a negative one. Are we all happy with this?
Sorry, sir.
Yes.
Apologies. Can we just confirm with that value for the first one there, 29,400? I get 29,430.
Okay.
Maybe I might be mistaken.
Yeah.
Is that
Yes.
Roselle, eh?
You also
Okay,
got
That's
that.
correct, yes, sir.
The first one, eh?
Yes.
sir.
Yes.
First one.
Okay. Mr. Moses will, yeah, you will, that's got it from him, I think. 29430, like that.
Yes, like that, sir.
Okay.
That's
Maybe I wrote
correct,
it wrong.
yes, sir.
Okay, cool. The people are paying attention. I was worried. Okay, cool. So let's quickly pump this into the thing. What I want to do is I want to check my equation here, which I haven't used in a while, and see what's going to work out. This one. Just copy him so long, just paste him over here. So I want you to populate that in the quadratic equation. Where are you? Down here. Yeah, sorry about this. Just want to bring this down so I can see it here for myself. I believe this might work. Should work. Okay. Yeah, there we go. So yeah. So you just check the two stress values. So there, what you're going to find is obviously that the value is going to be higher than all the other two values combined. So that's 30 kilonewtons. And then it's a 706. See, 1 plus root of 1 plus, okay, 2 times 2. I'm assuming we all can use the quadratic equation.
Yeah.
Okay. You never know, man. You know? Our area is 7.858. -6. What's -6 times the height of 0.1? And that's P was 30 kilonewtons times the length of 8, right? Let's have a look here. Yo, damn. It's Friday. Friday already, huh? Let's see what you get there. I'm gonna check my answer. I've got an answer using that formula. And then I just want to check quickly. Let me see. Cool. So what do we get? Is it a 1 or a L? Not sure. I think it's an L. What did we get over there? It's like my equation worked out. Yeah, no, my equation didn't work out. I thought it would work out. What did we get? So let me quickly see here if I use my Casio over here. I don't know if you guys are aware that this Casio is able to solve quadratic equations. Let me just see. Can this one also do it? Just check. Menu, complex space, matrix, vectors, stats, spreadsheet, table, equation. There we go. Let's try this one. Simultaneous is 1. Amount of unknowns is no, it's not simultaneous. This is something else. Okay, sure. Okay, cool. Are we winning with this one? What is it called again? What are we doing? We are doing a quadratic equation. This polynomial decrease to this is gonna be 1.359. Are you guys doubting yourself? You guys need help? -14, eh? That's the one coefficient. The next one is 1.32. 1132. -5. And then the other coefficient is -29430. Equal, but it's equal. I don't see the same answers as the book. Are we sure all our coefficients are right here? I typed this right in. Can I just check this one over here? Mr. Moses, are you there? Kagiso, Leon. Let me just go check this one. 706.858. -6 times 8. 2 times 208. -9. Cool. 1.359. Okay, that's right. I believe everything is right. I didn't work. Guys, are you winning? Guys are awfully quiet there.
The answer is the same as the book, sir. The book just gave it into MPA, sir, and the calculator gave it into Pascals.
Yeah, okay, so you got it. What is the answer? There should be two answers, right? It's a positive and a negative. So what did you get?
Like 480 million Pascals
Yeah.
for the plus, and then for the negative, like the 1 billion, I believe. So
Yeah, so what you just do, you just press the engineering notation to make it easy for yourself, man. You know, you don't have to say all the, yeah. And we normally take the positive value. Did everyone else get it? Mr. Moses, the only guy who's got in there. 132, -5. Sarge is quiet, Rosel's quiet, Leon's quiet. What's going on? Thinking about giving up. 1.359 times 10 to the -14. Just check my coefficients. Is equal. Hey, enter. 832. These are not correct answers here. Let me just have a look. Values. Are we sure we have the right values? That's -14, right? Perfect. Yes. Okay. And then let's just redo this again. 1.359 -14. This is -1.132. It seems that I'm putting the wrong value. That's -29430. Sorry about that. I'm still not getting the right answer. It should be 480 apparently, right? Positive, negative, negative. Yeah, I'm not sure what's going on. Did we miss something here? We should get the answer. It's 2EAL. Yeah, it looks correct. What's the length of our bar? Is it 8 meters? Yes, that's right. Yeah, I don't know. Not sure what's going on over here. 1.39. It is -14, right? -5. Yeah, I'm not sure. We should get 480 apparently. I'm getting 194 here and 112. Okay. Guys, are we lost? Where are you? Where are you? Let me see here. So minus B has to be plus 1.132 times -5. Plus minus, just take this away. Okay, big B will be -1.132 times -5. We square this guy. -4 times 1.135 times -9. Times C, which is -29430. And we can extend that way, and all of this must be divided by 2 times A, which is 2 times 1.359. Okay. Anyway, that's what you should have done, and we're expecting 2 answers. You guys can tell me what those 2 answers are. All I'll tell you is you must take the positive value. You're taking the tensile value of the situation. Okay, guys. So I'm gonna end it there. No one's saying anything. Is there any questions? Sydney, Sazi, Roselle, Leah, Panankosi, Mr. Moses, Dagiso, Suma, Chanel. You guys have any questions? Are you stuck anywhere before I end the session?
So,
yes.
That activity 2.2, sir, where they gave you that one stressor, that 140 megapascals. So for that scenario, that megapascals were both for the gradually applied load and the suddenly applied load.
That is correct.
Because in the theory they explained to you that and logically speaking, that if the gradually applied load is twice if the suddenly applied load is twice the amount of the gradually applied load, that means the stress would also be 2 times that amount.
Times more. Yeah. No, I'm just saying it's this particular question, man. You know what I mean?
Okay.
It's not like you know what I mean? It's for this particular question. Yeah, it's the way they word it.
Because after that question, sir, I started to attack everything like that question, sir. That was
it's not. No, it's not the case. The case, if you look at the stresses, you notice 42, 84. And I see what you're saying, because now you're saying it's the same stress. But I think for that particular question, how they're wording it, man, they say if you read the question, so that the elastic limit is not more than the allowed, man. So they're kind of telling you that is the limit for this particular question. But like I said, that's a very theoretical type question in terms of what's supposed to happen. But as you see here, 42, 84, and I believe you should get 480. So the concept is, depending how you're doing this loading, it's completely different. Yeah. Anything else?
So sorry, sir.
Yes.
The way you calculated stress using your impulsively or impacted load formula,
Yes.
sir. Did you
Hmm.
derive that from the quadratic formula, so or how did you derive that equation?
This one here. This one
Yes.
here. Yeah, so the other one I just tried now and I didn't trust it. So I just want to verify something, man. Let me just go to one of my other favorite textbooks for Stentor materials. And I used it long time ago. I just cannot recall. And I think I like that you're asking it because obviously if you have a shorter way of solving it, why not, right? It's coming from the quadratic here, definitely. Let me have a look. I think, Mr. Moses, you're making everyone like super scared. Yeah, because I don't know if they
I
prepared
was I'm then
as
giving
much
the
as
wrong
you.
values, nothing to be afraid of.
They were like, oh, flip, this guy's gotten to this point. This is one of the books I use. I'm gonna find the state energy thing now. What I realize of a lot of the things, man, if you don't study all the way, you tend not to see the value of a lot of the stuff we do. Oh, what am I doing here? Where am I now? Okay. But nevertheless, let's try and this is temperature stuff. Looking for strain, eh? Where am I now? Strain analysis. This is strains in 3 dimensions. Oh, yeah, this is my standard diagram, fact of safety, elastic constants, no. 3-dimensional stresses. Yeah, there are 3-dimensional stresses, yeah. There you go. Kramer's rules also used here if you're doing maths N4. But let me see if I can find strain. No, compass. Let me just go back to the contents. You know, I have this bad habit of always looking in the book instead of just going to the contents. Give me a second. No, let me just go back. No. Just wanna check where strain is over here.
And
I can.
so another question, sir.
Yes,
That
okay.
in the strain energy, no, not the strain energy, or yeah, maybe I think it is that bolt, referring to that bolt being tightened and being compressed. So, do I treat that bolt specifically the same as I would treat stresses regarding what's the thing called series plays?
Yes. Yeah, there's equation. There's equation. There's it. You see there? That's the one. I'm gonna check it now. That's did I solve that question before? Did I send you a video with me solving that question? Mr. Moses.
I can't recall, sir.
Okay, I'm gonna check. Just post it in the group. Anyway, there's the equation. Yeah, it is here. And I really appreciate you. Can you see here the stress squared 2WA, whatever this over here? It's coming from the quadratic. Here it is. There's it. It should work. In the case of a sunny applied load. But is this the impact load one? Let me just confirm. Yeah, it's the same thing. So just remind me I want you to try this out for me to see if it works. No, I'm gonna take a picture. But then just post some questions in the group so I can answer. No, if you have questions.
And so just one more question with this formula, sir.
Yes.
That half at the bottom of the quadratic formula is 2 times A, and the A that they took out there was the stress.
No, A is the area. Just focus on this
Area.
one.
Okay, sir. Okay, yes, sir.
Yeah. So what they done was, obviously you can see they just put in the coefficient, this B squared, you know what I mean? That's 4AC, you know what I mean? It's the same thing. And then the 1/2 is
Yes,
divided by
yes,
2.
sir.
Yeah. Why is this here? Okay, I'm pretty sure I can figure. But anyway, try that out and let me know if it works. It should work, man. I know it works. It's just yeah.
So just a question. I'm now looking at this this equation we were busy with. We said here almost now we were saying W times G. No, M times G, but we already have the whole force, so why would we multiply by 30 times 9,8?
Yes, thank you.
Yeah.
Yo, yeah,
So,
yeah, that
Yeah.
slipped my mind as well. Yeah, exactly. So guys, there we go. There's no need to times by 9.81. No, there we go. That's the issue. There we go. There we go. That is the whole issue. Yeah, thank you. I didn't even see that. That's the main thing. Are we all happy with that? Right. So we just have to adjust all these values now. Cool. What completely slipped my mind. 30 kilonewton. So therefore, this is going to be, what's this? Times 0.1, 3,000 exactly, yes. And then the other guy would be 30 kilonewton times 8 divided by the 208. There we go. Thank you for picking that up, man. And that's going to be 1.15, 4. Just call it 4 times 10 to the negative 6. There we go. If you have that, everything should work out. So you just gotta put everything where it needs to be. Yeah, there we go. Perfect, man. I was wondering, man. It's like, why is it not working out? But that's it. There we go. Nothing more, nothing less. Just erase this over here. Okay, guys, let me know solve it. And then post some questions in the group as well if you're lost. Maybe you can do that later on tomorrow on Saturday or Sunday. Yeah, and then I'll try to my best to answer as much as I can. Okay, guys, thanks, eh? Mr. Moses, just remind me of the bolt example as well. Yeah.
Thank you, sir.
Cheers. Yes, Kagiso.
Are we gonna have our sessions every Friday?
I don't know what's the best date. But for me, yeah.
Okay.
Is it Tuma who's talking?